Equilibrium constants are going to depend on the temperature of the reaction. So what we'll see is that the temperature is often specified, like it was in a couple of the previous slides where it says that this is the equilibrium constant at 25 degrees Celsius. But the temperature is not part of the expression. So just don't worry about it. It's sitting there, but that does not mean that you need to use the temperature in your calculation. Concentrations should always be in moles per liter, but we usually just drop the concentration units, and we have the equilibrium constant being unitless or dimensionless, because different reactions would have different combinations of moles cubed per liters cubed and all kinds of crazy things like that that don't really mean anything anyway. So to make things simpler, we just said we're just going to ignore the molarity units there. So the concentrations of reactants and products will not always be the same for a given reaction, but the equilibrium constant will be the same at a given temperature. So you can change the reaction, you can put it in a larger container, you can add water to it, you can change the concentrations, but the constant will be the same. So let's look at this reaction. Hydrogen plus iodine forming hydrogen iodide. So suppose a mixture of H2 and I2 is allowed to come to equilibrium at 445 degrees Celsius. The measured equilibrium concentrations are, so the hydrogen ion concentration is 0.11 molar, I2 is 0.11 molar, and HI is 0.78 molar. What's the value of the equilibrium constant? This is, in a word problem, how they calculate, how they determine what those equilibrium constants are. They actually do the reaction, they measure the concentrations of all the reactants and products, and then you throw it into the equilibrium expression. So the first thing we have to do is write the equilibrium expression for this reaction. So KEQ is the concentration of the product. Here there's only one. It's in the gas state. So we've got HI. And the coefficient is 2, so that's going to be squared. And that's going to be divided by the concentration of the reactants. So we've got H2 times I2. And both of those have coefficients that are 1, and so their exponents are 1. So I've got this equilibrium expression. In this problem, they're giving me the concentrations, and so I'm going to plug them into my equation. So HI has a concentration of 0.78 molar squared. You can write the capital M in there if you want to, but we're going to drop it at the end anyway. Divided by H2 has a concentration of 0.11, and I2 has a concentration of 0.11. So be careful on your calculator. So I've got 0.78 squared divided by 0.11 divided by 0.11 equals. And we will consider significant figures. Each of these concentrations has 2 significant figures, so I'm going to report the equilibrium constant with 2 significant figures. And so I'm going to say it's 50. 50 decimal point, or 5.0 times 10 to the 1. No unit on the equilibrium constant. Any questions? If you're going to do this on your calculator and you want to multiply these, let me put a different color in here. Divide and then parentheses times this close parentheses. Just make sure that you're coming up with the number 50.28. Otherwise, you're miscommunicating with your calculator. This is a graphic from the book that I wanted that they didn't include with all the others, and so I took a picture of the book. Like, seriously. This table is about the same equation that we were looking at the same temperature. And so the equilibrium constant, we calculated it, was 50. And so we did this calculation right here. What if we started with 0, we started with none of the reactants and 0.5 moles per liter of the product? And we let the reaction go. Initially, you're only going to have reverse reaction. Eventually, though, is going to reach equilibrium. And these values would be determined experimentally. You'd measure the concentrations. When we take those values and plug them into our expression, we get the same constant. That's why it's a constant, because it doesn't change. You could start with equal amounts of all the reactants and products. At equilibrium, this is what you would get. When you plug those in, you still get an equilibrium constant of 50. So the concentrations of reactants and products may be different, but the equilibrium constant is always the same. Okay with that? One person is. So consider this reaction. Carbon monoxide reacting with hydrogen to form, this is methanol, CH3OH. So a mixture of these three things is allowed to come to equilibrium at 225 degrees Celsius. The measured equilibrium concentrations are, and they're given right here. What's the value of the equilibrium constant at this temperature? We're not going to use the 225 in a calculation. It's just there. This is the temperature, because they said. Never. Nope. Well, to calculate the equilibrium constant, we need the expression. KEQ equals, so concentration of the product, CH3OH. The coefficient's 1, so the exponent is 1. Divided by the concentration of CO. The coefficient is 1, so the exponent is 1, times the concentration of hydrogen. There, the exponent is 2, because the coefficient is 2. There weren't any solids or liquids, so they're all being included. Yes?
So if the product was like only a solid, the equilibrium the constant is 0 then?
No, it would be 1 over the concentration of the reactants.
Okay. So if you have anything to put in, you just put in 1.
Mm-hmm.
Okay.
So now, because we're calculating KEQ, we're just going to take the values that were given and plug them in. So methanol concentration is 0.151. So that's, well, either the concentrations will be given and you'll be asked to calculate the constant, or we'll give you the constant and all but one of the concentrations and ask you to calculate that.
How do you do that?
That's coming up next. So 0.151, and the CO is 0.489, and the H2 is 0.146, and that one is squared.
How do you square it?
Use the x squared button, or divide or multiply by it twice. So on my calculator, this is what I'm doing. 0.151 divided by 0.489 divided by 0.146 x squared equals. And I'm getting 14.486. All of my concentrations have 3 significant figures, so I'm going to report the constant with 3 significant figures. Another way you can enter that into your calculator is 0.151 divided by, open parentheses, 0.489 times 0.146. And then you could either press the x squared button, or you could just multiply by 0.146 again, close the parentheses and press equal, and you'll get the same answer. If you're having calculator issues, please come and talk to me separately, and I'll have a word with your calculator. It's the calculator's fault. It's not your fault. So calculating KEQ is all nice and everything, but why would we even need to know that? The reason that KEQ is useful is because we can use it to predict what concentrations are going to be. Some things are very difficult to measure, but we need to know the concentration. So we can use KEQ to calculate equilibrium concentrations. So here's this equation. 2COF2 reacts to form CO2 and CF4, and the equilibrium constant is 2.00 at 1,000 degrees Celsius. So KEQ is equal to 2. Is this reaction going to favor the forward or the reverse reaction?
Forward?
Forward slightly.
How are we able to that again?
Because KEQ is close to 1. So that means it's more of a half and half in the middle. It's not a really big number, which would favor the products. It's not a really small number that would favor the reactants. We're given the concentration of the reactant and one of the products, the CF4, and we are asked, and we're also given KEQ, and we're asked to find the concentration of CO2. So what we're going to do is we're going to write the equilibrium expression, and then we're going to rearrange it and solve it for this thing that we need. So first is writing the expression, KEQ equals concentration of the products, CO2, exponent is 1 because the coefficient is 1. CF4 also has a coefficient of 1. Divided by the reactant, concentration of COF2, and that has a coefficient of 2, so this one's squared. I want to rearrange this equation so that I get CO2 by itself. So some of you can do that in your head or by mumbling to yourself, and some of you have a hard time with this. So I'm talking to the people who have a hard time with this. This equation has a fraction in it. Let's cross multiply and get rid of the fraction. And you might say, well, how can I cross multiply? I only have a fraction on one side. Well, we can make that into a fraction. That's KEQ divided by 1. There's a fraction. So I'm going to take 1 times this. So that's going to give me CO2 times CF4. That is going to be equal to KEQ times COF squared. You okay with that? I just cross multiplied. I want to get CO2 by itself, so I'm going to divide both sides by the concentration of CF4. Concentration of CF4 over CF4 is 1. It cancels out. You okay with that? Now I have CO2 equals this mess. I know what KEQ is, I know what COF2 is, and I know what CF4 is. So I'm going to take those numbers and I'm going to plug them into the equation and math. 2.00. COF2 is 0.255. That is squared. And divided by CF4, 0.118. Two times 0.255 squared divided by 0.118. So the concentration of the carbon dioxide is equal to, I'm going to check my sig figs, I should have 3, 1.1021. So 1.10 moles per liter. The equilibrium constant does not have units, and we're not going to use units in the equation, but we understand that this in brackets means that the concentration is always in moles per liter. Any questions? Let's do another one. Diatomic iodine decomposes at high temperature to form to form iodine atoms according to this reaction. Here's KEQ, 0.011 at 120 degrees Celsius. In an equilibrium mixture, the concentration of I2 is 0.10 molar. What is the equilibrium concentration of I? We'll just start by writing the expression. KEQ equals, both of these are gases. We're going to have the product, which is I, and the coefficient is 2, so that's going to be squared, divided by the reactant, which is I2. You can see how you might mess that up, right? There's I's and there's 2's, and some of them are above and below and in and out of the brackets, and you just got to be careful. What am I trying to find? I. Trying to find I. So I want this one. Again, we've got a fraction there. So let's cross multiply, get rid of the fraction. So 1 times I squared is going to equal KEQ times I2. You okay with that? Now, I squared equals this, but I don't want I squared, I want I. Square root. I need the square root of this. So I'm going to take the square root of this side, and I'm going to take the square root of the other side. So the concentration of the iodine atoms is equal to the square root of KEQ times the iodine concentration, the molecules. So that's the square root of KEQ, 0.011, times, so this is the concentration of I2, 0.10. Calculators look at this differently, but you need to be taking the square root of 0.011 times 0.1. So you got to figure out how your calculator wants you to put that in. So you should come up with 0.033 moles per liter.
So how do you put it in there?
Depends on what calculator you have. So that's a better question to ask me in lab. You should have a square root button on your calculator. On my calculator, I press the square root first, and then I do the 0.011 times 0.1 and press equals. On some other calculators, you may do 0.011 times 0.1 equals, and then press the square root button. So if it didn't work the first way, try the second way. If it still doesn't work, come see me in lab.